Hi everyone. So let's start. Before we just start, I think it would be great if I get to know whether you guys can hear as well as see me properly. So if you can hear and see me properly, you can just type in a yes, and then we can begin our session. Okay then, great. So that means we can start. So today we are going to learn a specific topic rather than solving a specific problem, and that is going to be recursion. Okay, cool. So my first question to all of you is that how many of you are afraid of this topic? How many of you don't feel so comfortable with the concept of recursion? You can say yes if you belong to this category. Okay, so I can see some people saying a yes. So the purpose of this class is to first make sure that you are very good with the fundamentals of recursion, and then we'll even pick a good quality question and solve that using whatever we have learned today. So quick question to everyone: what is recursion for you? How do you define recursion? So there can be multiple definitions to it. I will talk about it in a very practical manner. So, recursion is all about delegating a task. So it means that, let's say if you have a big task and you don't want to do it all on your own, then you can delegate some part of it to somebody else. Now that somebody else over here is a function call. To give you a very quick example, all of us know what is n factorial. N factorial is nothing but the product of first n natural numbers, correct? Now as you are looking at this expression and specifically this side of it, I can say that, hey, this part looks to me as if it is product of first n minus 1 natural numbers. So if you are saying that n factorial is the product of first n natural numbers, then you can also say that n minus 1 factorial is the product of first n minus 1 natural numbers. So that means it can be written as n minus 1 factorial multiplied by n. Now if you look at this expression, it has a lot to say. What it basically is saying is that, hey, if you want to know the factorial of a number n, then you should first somehow figure out factorial of a smaller number n minus 1. Because if you know that, you can simply multiply it with n and you will get your result. For example, to get the value of 10 factorial, I would just want to somehow know the value of 9 factorial. Now let's say I do not take the responsibility of calculating 9 factorial. I can tell somebody else to do that for me. And if that somebody else does it, I can just get the answer, multiply it with 10, and that will give me the 10 factorial. So what is it that we have done? We simply have delegated the task. We have delegated a big task to somebody else. So we said that I'm not going to, perform all these multiplications on my own. I am just going to perform the last multiplication. This multiplication somebody else should do. This kind of equation or this kind of mathematical relation is also called as recurrence relation. So recurrence relation is nothing but it's an equation that relates a larger problem to a smaller sub-problem. So I can just say that n factorial has a dependency on n minus 1 factorial. And this is not something very new to you. You must have solved problems like Fibonacci numbers. For example, when you solve for Fibonacci number, you say nth Fibonacci number, which is f of n, is equals to f of n minus 1 plus f of n minus 2. What does it mean? It clearly means that it has a dependency on smaller subproblems. So if I first solve for this and this, then I can easily solve for this thing. That's the idea of recurrence relation. And I would say the most important aspect of any recursive solution or recursive code is recurrence relation. How you relate a larger problem to smaller subproblem. We will see a lot of examples of this, but is this idea of recurrence relation absolutely clear to everyone here? If yes, you can quickly type in a yes. Okay, awesome. Now, there is another important aspect of recursive solutions. The first thing is recurrence relation, but tell me one thing. Will this equation hold if the value of n is, let's say, 0? Will you want to write that 0 factorial is equals to minus 1 factorial into 0? The answer is no, because minus 1 factorial is senseless. It does not make any sense. It means that whatever equation we have, that equation does not hold for all the values of n. It will hold for the positive values of n, but not if n is 0. And we all know that 0 factorial is 1. So we would say that, hey, if n is 0, then that's just like a special case for me. In this case, I got to return 1. I do not have to apply this equation if n is 0. Correct? This thing is called as a base condition, or you can also call it as termination condition, because this is when your recursive set of calls eventually terminate. So I would say there are two important aspects of any recursive program. The first thing is recurrence relation. The second thing is your termination condition or base condition. Everyone feels clear with the idea of base condition? You can respond saying yes or no if you do. Okay, great. So now that we have a recurrence relation in place and a termination condition in place, so it's super easy to write any recursive program. I can simply say that, hey, I want to find factorial of a number n. So this is the function that we'll have. Now there is nothing special that we have to do. We would say that to find factorial of number n, I would somehow want to know factorial of n minus 1. And I would then want to multiply this thing with n and return that. So your recurrence relation has been coded over here, right? But we all know that recurrence relation would not apply for all the values of n. So we would say that, hey, if the value of n happens to be 0, return 1. And it's always a good practice to first write your termination condition and then write your recurrence relation. You will shortly understand why, because when I go ahead and draw the pattern in which recursive calls happen, it will give you a clarity why we do something like this. So, you know, if you look at how the recursive calls basically happen, let's say you have been given a number n and that number is equals to 4. So if you want to determine factorial of 4, and if you go by this code, you would say that, hey, 4 is not equals to 0, so I would come here. Now when I come here, I can immediately see that there is a function call being made, and that is being made for 4 minus 1, which is 3. So I would end up calling f of 3. With the same logic, when f of 3 is called, it would end up calling f of 2. And then it would call f of 1, and finally it would call f of 0. Important thing to understand is that the moment f of 0 has been called, this condition will be true and you would end up returning a value that is 1. Correct? Now, if you think what had happened when f of 1 was called, let's go back in past. When f of 1 was called, you came here and you ended up calling factorial of 0. Now when factorial of 0 has returned you a value 1, what is it that you are supposed to do? You are supposed to simply multiply 1 with n, which was 1 here. So you'll simply multiply this result with 1 and you will return that to your caller. Similarly, if you remember about f of 2, it was waiting for the return from f of 1, which it has gotten, and now it would multiply it with value 2, which is this, and return that to its parent. So it would return 2 into 1 into 1. Similarly, f of 3 would multiply 3 to the result that it has procured and simply return that to its parent. And similarly, f of 4 would multiply 4 to this result and return that to its caller. If you're wondering who would be caller of f of 4, there is always a main function from which you make your first call. So I can imagine there was a main function here which had made a call to this, and finally this main function has gotten the product of first 4 natural numbers, which actually reflects the value of 4 factorial. So this is how control flow happens in recursion. So there is a function which calls another function, which calls another function, which calls another function. So the call flow happens from top to bottom. You go from n to n minus 1 to n minus 2 all the way till 0. But how does the return happen? Return happens from bottom to top. You first eliminate this, then this, then this, then this, then this. This is one of the reasons because of which your operating systems go ahead and use data structures like stack to implement recursive calls. Because stack is a last in first out data structure, and the same behavior is expected over here. What sort of behavior? The function which is called at the last should be removed at the first, last in first out. Okay, is it clear so far to everyone that how this call flow looks like and why stack is the ideal data structure which is used to implement recursive calls? Okay, that's great if it does. Now, as I told you, the first aspect of any recursive solution was recurrence relation, correct? So what we will do is, we will try writing some recurrence relations. Now let me tell you, for a given question, there is no fixed recurrence relation. You can have multiple recurrence relations, okay? For example, let's eliminate this code for now. And let's talk about an even simpler question where you have an array whose size is n and it contains some elements. So these are the different elements at different index. This is index 0, 1, 2. This is index n minus 1 and this is index n. If somebody asks you to find the sum of this array, you can simply do that by writing a for loop. And that for loop would work in order n time and you'd feel great about it, right? If I ask you to write a recursive code for it, how would you go about it? How would the recursive solution look like? So I would say whenever you have to write a recursive solution, do not immediately jump on towards writing the code. First, take a piece of pen and paper and think about what sort of recurrence relation do you see. And if you see that recurrence relation, is there a base condition? Are there multiple base conditions? So write those things down and then only go ahead and write your code. That way you will get your code correct in the very first step itself. So see, if I have to write the recurrence relation for it, I would say, hey, this is going to be super easy. Why? Let's think of it in this manner. Let's say there is a function called as sum. And this sum, it takes your complete array. When I say takes your complete array, it's take the starting index and the ending index. So the starting index initially is 0 and ending index is n minus 1. This size is n, so it would better be n minus 2 and n minus 1. Yeah. So if we have to find the sum of this array, this entire array, then I can say that, hey, if somebody tells me the sum of this much part, which is from index 1 to n minus 1, then I can simply add to it the contribution of first element and that will be my answer. So this is one recurrence relation which absolutely makes sense, right? Because we can say that, hey, the sum of this entire part is equals to this element, whatever it is, plus the sum of remaining part. Whatever I have spoken is mathematically written over here, and it can be translated into any programming language also while writing the code. So this is the recurrence relation that I have here. Now think of it in this manner. If I go ahead and try writing this piece of code, is there a termination condition that I should be thinking about? If yes, then what? What should be my termination condition? If n is equals to 0, then return array of n. Okay, that is what one of you is saying. See, what is happening over here? As you are making recursive calls, the size of your array is reducing. So first you would say that, hey, I need the sum from index 0 to n minus 1. Then you would say that, hey, I need the sum from index 1 to n minus 1. Then you would say that I need the sum from index 2 to n minus 1. You'd keep going on and on and on. And finally, you would say I need the sum from index n minus 1 to n minus 1. So basically, initially the size was this. Then it became this much. Then it would become this much. Then this much. And finally, it would just be this, which only denotes the last element. Now, if you are talking about a subarray which only has one element inside it, then this equation will not hold for that. Because in that case, there is no remaining part for it. So imagine if just this much part is your input, then I can say that, hey, there is no remaining part to it. So I would say that if I ever encounter, if I call this index as I, then the equation will be written in this manner. Then I would end up saying that, hey, if the value of I is equals to n minus 1, that means such kind of situation is there. Here, the sum of that part is simply equal to the value of array n minus 1. So this is going to be my simple termination condition that I can write, and my job will be done, right? So I can say that, hey, I can very easily imagine a function func, which takes probably a start index and an end index. I'm just writing kind of pseudo code. You don't mind the signatures and all. And what I would say is that if I need to know the sum from index S to index E, then I can simply use this idea, right? I can say that, hey, this is simply going to be func S plus 1 to E, which is going to denote the sum of the remaining part, plus array of S. This is what I have got to return. And what will be our termination condition? So you can note one thing, E is never changing. Why? Because E is the last index. The last index is not changing at all across all these function calls that we are making. So I would say that, hey, the moment I see that S is equals to E, that would denote that we have reached the end, and then there is no remaining part. So I would say that the moment S has become equals to E, I can simply return array of S. That's it. So you can see that whatever work I did here, I could easily copy paste that in form of code, and the basics are still the same. There is a recurrence relation, there is a termination condition, and whatever you get as a result of that is your recursive solution, as easy as that. So recursion is easy. What is hard is to figure out your recurrence relation. Now, as the complexity of problems change, finding recurrence relations takes you some time. Finding termination conditions also take you some time. So we'll dive deep into that in a matter of time. We'll also solve some questions to see that coming up. But is this idea so far clear to everyone? How many of you understand it? Okay, awesome then. So I told you one thing at the beginning, that we can have multiple recurrence relations. Any one of you who was able to come up with some other recurrence relation for finding the sum of array? So I would suggest a different recurrence relation, and then you guys have to think a bit about it. Let's say I want to find the sum of array, and the array is from index 0 till n minus 1. So I'm going to think little differently here. In the previous solution, I was just snatching away the first element and then I was recursing on the remaining part, correct? But how about doing something like this? Let's say if this is your array, I would say let's pick the first element and the last element, which is a0 plus a n minus 1, and then recurse on this part, which is sandwiched in between your selections. So what is that sandwiched part? That sandwiched part can be denoted as the sum from 1 to n minus 2. So this is little different from the previous approach. I am snatching an element from the front end as well as rear end, and then I am recursing on the sandwiched part. Logically speaking, the last recurrence relation was also right. This recurrence relation is also right. Yes or no? What do you guys think? Is there any logical flaw with respect to this recurrence relation? No logical flaw. The brain understands it's right. Okay, cool. But will it have an impact on my code, on my implementation? Specifically, will it have an impact on my termination condition? How many of you feel it will have an impact? So I'll first write the relation corresponding to it. In fact, I wrote it there, so I think no need to write it again. I would probably try to generalize it. Let's say if this index is I and that index is j. So what does it denote? It denotes that there is a subarray that you are considering. Let's say this is a subarray. This is just a part of a big array which starts from I and ends at j. If I need to find its sum, I would extract the first and last elements, which is ai plus aj, and then I would focus on the sum of this sandwiched area, and it can be expressed as sum from I plus 1 to j minus 1. So this can be our super simple recurrence relation. So let's say I want to write a function func which takes the starting index and the ending index and returns me the sum. I would say I'll follow this rule and I'll return a of I plus a of j plus func from I plus 1 till j minus 1. What about the recurrence relation? I would like to hear from all of you. For what relation should I terminate? Okay, see, if you are confused about how to find out termination condition or base condition, I would say you just have to look at the pattern in which the function calls are actually being made. So let's say you had an array like this. Okay. To start with, you wanted to find the sum of this, which was from index 0 till index 4. After extracting this and this element, you wanted to find the sum of this, which is from index 1 to index 3. After extracting this and that, you wanted to find out the sum of this, which is from index 2 to index 2. What does it mean? Index 2 to index 2 just denotes this much of the subarray. Now, when you are talking about just this much of the subarray, where starting and ending indices are obviously the same, would you want to go ahead with this expression? The answer is no. It would be stupidity to do that. Why? Because even if you do something like this, you will end up taking the same element twice, because your starting index and ending index both are the same. So your ai and aj both will be the same element. So by mistake, you would end up counting the contribution of that element 2 times. So I would say whenever I and j are equal, if my I and j both are equal, in this case probably nothing is to be done. I simply just need to return the value of that element, array of I or array of j, whatever you write, because both of them are Same. So this is one termination condition which kind of works for me. But I want you guys to think, is it sufficient alone, or do I need to probably add few more termination conditions to it? So a lot of you are suggesting that we would need one more, okay? Let's take example of another array. Let's say this was to be your array. Here, to start with, this is your array where your indices from 0, 1, 2, 3. So to start with, the value of I and j were 0, 3. Then you recursed on this part, which is 1 to 2. Now, when you had called for 1, 2, you'd have taken a of I plus a of 2, and you'd have made a function call for what? 2, 1. Now this does not make sense because starting index cannot be greater than the last index. And now when does it happen? It happens when you do not have any elements left. Because think of it in this manner, if you made a recursive call for a subarray of size 2, and if you already considered this and that, then there is nothing that is left. Because there is nothing that is left, so such kind of situation has happened, such kind of unacceptable relationship between the starting and ending indices have happened. So in this case, I just need to return 0 because it denotes an empty component, an empty subarray. So I would simply write that the moment I see that I has become greater than j, I would need to return 0. And if you are a little mindful, you will realize that this termination condition will be met when the size of array is odd. Like here there were 5 elements. So from 5 it became 3, from 3 it became 1. So when it became 1, I and j were equal, correct? And this termination condition would hold when the size of array is even. So I need to have both the termination conditions in place. So I want to connect so many dots over here. The first thing that I told you was, the moment you change your recurrence relation for the same question, your code changes and your termination condition changes. And as a consequence of that, you can even end up having multiple termination conditions, like the case over here. Does that make sense? How many of you completely follow me on this part? Okay. So far, so good with everyone, right? We'll see one more case. See guys, till now, we have only seen the situation where one function was calling exactly one function. So it never happened that we have one function which is calling multiple functions. Like even in the last recurrence relation, the code that I had written, this func was calling just one more func. Here also this func is just calling one more func. You know, I can just go ahead and probably think of a recurrence relation where a particular function is calling multiple functions. That can happen. And let's see how that can happen. So let's say you still want to find the sum of array, right? You want to find out the sum of this array. Can I logically say that the sum of this entire big array can be written as sum of this left half plus the sum of that right half? Can I say that? Of course I can say that, right? So let's say if the middle index was m, then I can say that, hey, this segment is from 0 to m, from index 0 to m, and the second segment is from index m plus 1 to n minus 1. So as a consequence of that, what I can say is that the sum of the entire array, which is from 0 to n minus 1, can easily be expressed as sum of the left half plus sum of the right half. Now mind it here a function is ending up calling two different functions. So the simple call flow that I showed you for factorial, that will not be the case here, because here a function is going to call two functions, and then again that function is probably going to call multiple functions. That is how the call flow is going to actually occur, right? But all of you understand the idea behind this recurrence relation, right? How it holds and why it holds. Okay, so if we go by it, we can quickly take example of some array and see. So let's say you have an array containing some elements 1, 2, 3, 4, 5, 6, 7 and 8. That's your array. Okay. Now you want to follow this rule. So I'm just going to erase it for a while. So this index is 0 and that index is 7. Now let's say there is a function from 0 to 7. So the responsibility of this function should be to give me the sum of this part. Now what I could say is that let's figure out a midpoint m, which is 0 plus 7 by 2, it's 3. So I can say that this is my first half from index 0 to index 3, and this is my second half. So I would end up making a function call from 0 to 3, and then I would end up making a function call from 4 to 7. Correct? Now again, because it's recursion, so it will keep on repeating at each function call. So here also I'll figure out the midpoint. What is the midpoint of 0 and 3? 0 plus 3 by 2 happens out to be 1. So you'd end up making a function call from 0 to 1 and from 2 to 3. Similarly here, the midpoint happens to be 4 plus 7 by 2, which is 5. So you'd end up making a function call from 4 to 5 and from 6 to 7. And repeat it again. Here the midpoint happens to be 0 plus 1 by 2, which is 0. So the first call will be from 0 to 0. The second call will be from 1 to 1. Here 2 to 2, 3 to 3, 4 to 4, 5 to 5. Similarly here it will be 6 to 6 and 7 to 7. This is the control flow of recursion for the code that we wrote. Is it making sense? How many of you are able to make sense out of this diagram that I have drawn? Okay, if you can, that's great. Okay, how about these function calls? These all can be thought of as our termination conditions, don't you think so? Because what does it mean? F from 3 to 3, index 3 to index 3. It's just denoting a single element. So if you are just talking about a subarray which is comprised of single element, the sum of that is that element itself. So I can just say that if the starting and ending indices are same, we can just return that element itself. So what is array of 0? Array of 0 is 1, so we will return 1 from here. What is array of 1? Array of 1 is 2, so we will return 2 from here. Now if you remember, the code we had written was something like this, that f of I to j wanted to know f of I to m, so this was the left half function call, and then it wanted to know f of m plus 1 to j, which is the right half function call, and then it wanted to add the two results. So this got 1 from here, got 2 from here. When it does 1 plus 2, that will be 3. So the answer of this will be 3 and it will return that. Now it is doing its work perfectly well, because from index 0 to 1, the sum really is 3. Correct? Okay. Now if you look up at this and that, f from 2 to 2, what will it return? It will return the element at index 2, which is 3. Similarly, it will return the element at index 3, which is 4. And now what will it return? 3 plus 4, which is 7. And it makes absolute sense, because the sum from index 2 to index 3 is actually equal to 7. Now if you look at it, it will return 3 plus 7, which is 10, which again makes sense, because the sum from index 0 to index 3 is actually equal to 10. So this is how the values are being returned from bottom, and they are being propagated all the way till the top. So if you look at it, this left half has successfully computed the sum of left half. Similarly, this right half will successfully complete the sum of this right half and return it, whatever that sum is. And then finally it will return the answer. Did you understand this call flow and how returns are happening and all such sorts of points? Yeah, by the way, this idea is also popularly known as divide and conquer, because in reality what we are doing is we are dividing a large problem into smaller sub-problems, right? This was a large problem and we have divided it into smaller sub-problems, and then we are conquering their results. So if you go by this, you can actually write the code and it will be super easy. Let's say there is a function func and you want to find the sum from index I to index j. You'd first write your recurrence relation. You'd say that if I and j are equal, simply return a of I. Otherwise, what do you want to do? Otherwise, you first want to figure out the middle point. So the middle point is I plus j by 2. And after that, you want to first make a call to the left half, and then you want to make a call to the right half. So you want to make a function call for I to m, and then you want to make a function call for m plus 1 to j and return this value. So this is the code. Can you guys relate with the code? Do you see that the logic is very consistent with the lines of code? Yeah. So far whatever we have covered, does it give you little clearer picture of recursion than what you probably had before the class? Does it all help at the basic level? Especially to those of you who said that you're kind of afraid of recursion. Okay, that's great. Now the next thing is that there is something that I want you guys to think of. Take it as a food for thought. See, if I have to write a simple for loop to compute the sum of array, I can do that in order n time. What will be the time complexity of this function? Because at the end of the day, it is also finding sum of an array. So is it still order of n? Or is it greater than order n, smaller than order n? What do you guys say? Something that you guys should think of, and then probably we can discuss. Now we'll take up a question, a challenging question. Okay? Have you guys read it? It is there as a part of your video description. So the problem says that we are going to probably have a family of strings. And this is going to look something like this. So string 1 is just 0. Okay, just 0. Now, there is a rule. That rule says that in order to determine the next string, what you have to do is you have to look back to the previous string. And as you are looking back in the previous string, you have to convert every 0 in that to 0, 1. And if there is any 1, you have to convert that 1 into 1, 0. This is the basic rule that you have to follow. So if I follow this rule, in order to figure out S2, I'll have a look at S1. I can see that, hey, S1, it contains 0. So I need to modify this 0 to 0, 1. So I'll put 0, 1 here. And then S1 is over. Nothing is left in S1. So whatever I have is my S2. Now, if I have to create S3, I will look back to S2, which is this. So the first character is 0. And I know 0 needs to be replaced by 0, 1. So I'll put that. The next character is 1. And we know 1 is to be replaced by 1, 0. So I'll put that. So that is what your S3 is. Similarly, what will be our S4? Now I think it should be a breezer for you, right? If you want S4, you look back at S3. You see that this is a 0. 0 is to be replaced by 0, 1. 1 is to be replaced by 1, 0. 1 is to be replaced by 1, 0. And this 0 is to be replaced by 0, 1. Similarly, can you guys figure out S5? Can you guys type in the value of S5 on your own in the chat box? Let's just do that. And then I'll talk about the question, the real question. Let me do that in the meantime. You will have 0, 1 and then 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 1, 0. This is what your S5 will be. Okay, so what is the question? Let's come back to the question. The question is you have been given two integers, n and k. N and k. Now, you have to tell me the kth character of nth string. Kth character of nth string. This k could be 1 indexed, 0 indexed, anything, that does not matter. If it is 1 indexed, you can convert it into 0 indexed by doing minus minus. So for me, let's say I'm assuming this to be 0 indexed. So if somebody tells me that, hey, the value of n is 5 and the value of k is 4. So it means that he's asking me to tell him the fourth character in S5. This is our S5. This is character 0. This is character 1. This is character 2. This is character 3. This is character 4. So the answer, the output is going to be 1. This is the intent of the question. They'll give you n, they'll give you k, and you have to tell the kth character of S of n. Is the question absolutely clear to everyone? Yeah? Okay, great. So what is the brute force approach? The brute force approach is that you can go on creating the strings, but if you go on creating the strings, that's definitely a brute force approach. Don't you think you will be out of memory very quickly? The answer is yes. Why? Because the size of strings are growing exponentially. The size of first string is 1 unit, then 2 unit, then 4 unit, then 8 unit. It's doubling. And why should it not double? Because for every character, you are giving birth to 2 more characters. I mean, for every 0, you are planting 0, 1, and for every 1, you are planting 1, 0. So if the previous size is, let's say, x, then the next size is going to be 2x. It means that even if the value of n is, let's say, 20, 30, 40, something like that, or even if, let's say, not even that much, even if it's little smaller than that, you will end up getting out of memory pretty quickly. So the idea is that generating the strings is not a wise option, definitely not a wise option. So in that case, what is to be done? We need to probably come up with a little brilliant idea. And what should it be? So let's try to understand that. I'll give you some hints around it, and then we'll together come over to a final idea to solve this question. I'll just remove this part, and I'll remove this part also, probably this entire thing. So what were we doing? We were converting 0 to 0, 1 and 1 to 1, 0. And we wanted to know the kth character of nth string. This was the basic requirement, right? Okay. Let's simply think of it in this manner. See, I don't know what my nth string is. I don't know it. But can I estimate the size of it? What will be the size of nth string? It's very easy. See, the size of first string is 1, second string is 2, this is 4, this is 8, this is 16. So do you see a pattern? the pattern is of 2 raised to power n minus 1. 2 raised to power 1 minus 1 is 2 power 0, which is 1. 2 raised to power 2 minus 1 is going to be 2, 4, so on and on. So I can say that the size of the string is going to be nothing but 2 raised to the power n minus 1. So we know that how many characters are going to be there. Of course, there will be so many. So of course, it will demotivate us from generating the string. I'm never going to do that. Now, coming back to how I solve it, I would say no matter which string you are talking about, it has been generated from 0 only. I mean, their godfather is 0 only. From 0 you got 0, 1, from 0, 1 you got 0, 1, 1, 0, from this you got that. So the highest ancestor is 0. So I can say that, okay, let's say your value of n is equals to 5 for now. And this ideally should be your string. You have not generated it still, but you know that this ideally should be your string. Now you have this thing in your mind that, hey, this thing is nothing but this thing is a expanded version of 0, because 0 expanded into this and that and that. Now you can start to think little clearly. You can say that the size of this thing is 16. We can know that by this formula. And then there are 2 halves of it. So the first half is 1, 2, 3, 4, 5, 6, 7, 8. Yeah, this is the first half. And that is the second half. There are 2 halves of it. Can I say that this half would have been a representation of 0 and this half would have been a representation of 1? Can I say it with surety? I would say yes. Why? Think of it in this manner. All of us are saying that this has germinated from 0, and now I can say this 0 has germinated into 0, 1. Correct? It has germinated into 0, 1, and then this 0 further germinated into this, and this 1 germinated into this, and then this germinated to that, this germinated to that, and then this germinated to this, and this germinated to that. So I can say that the left half of your string is actually going to be expanded version of 0, and the right half of your string is going to be the expanded version of 1. Is this point making sense to everyone? You can just say yes or no. Now, the beautiful thing about it is that you can simply go on recursing over this idea. You can literally go on recursing over this idea. What I mean by that is, if you look at this half in an isolated mode, just look at this left half, forget about the right half. Then you can say that, hey, because this is a representation of 0, and because 0 expands as 0, 1, 0 expands as 0, 1. So I can say that the left half of this would be actually an expanded form of 0, and the right half of it would be actually an expanded form of 1. And that is the case. You can see that this 0 expanded to 0, 1, and then this 0 expanded to this 0, 1, and this 1 expanded to this 1, 0, and then this 0, 1 expanded to that, and this expanded to that. So I can say that this is actually coming from 0, and that is actually coming from 1. So now this idea can even be applied there. How it can be applied there? We all know that 1 is broken down as 1, 0. Because 1 is broken down as 1, 0, so I can say that the left half of it would have germinated from 1, and the right half of it would have germinated from 0. And that really is the case, because if I ask you to compress this, let's say if you have to compress this, how will you do that? 1, 0 will go back to 1, 0, 1 will go back to 0, and we all know that 1, 0 will again go back to 1. So I can say that if you have a big substring with you which represents 0, then the left half of it would represent 0 and the right half of it would represent 1. So I'm just writing it down here. Let's say you have a big string, no matter how it looks, what it is. if this string represents 0, if you are sure that it represents 0, then the left half of it would be representation of 0 and the right half of it will be representation of 1. But if this string was to represent 1, then the left half would represent 1 and right half would represent 0. Why? Because such is the pattern that is followed in order to create these strings. Is this idea making sense? How many of you totally understand this pattern? So beautiful to observe, isn't it? So now I would say that there is not much left in this question. In fact, nothing is left. Let's say this is your fourth string. I'm just writing it here. Somebody had asked you to tell him the first character, k equals to 1. Now you'd say that, hey, let us first talk about the entire string. We all know that the entire string is a representation of 0, correct? And we know that its first index is 0 and the last index is 7, right? Let us figure out the middle index. What is the middle index? Middle index is 3. So I can say that from 0 to 3 is the left half and from 4 to 7 is the right half, correct? See, 0 to index 3 is the left half and 4 to index 7 is the right half. And we all know that this entire string is a representation of 0. In fact, every string is a representation of 0. Every final string, right? Now, where should this index lie? Does this index lie in the left half or does it lie in the right half? Tell me. Left or right? Index 1 lies in left half. Because index 1 lies in the left half, what would you want to say? You would want to say that, hey, the character that I am searching for, that character belongs in the left half of the string. And left half of the string is from 0 to 3. And now this represents what? It represents 0, because we know that the left half of 0 represents 0, correct? Now again you can repeat that thing here as well. You can say that, okay, now this is the part that I am going to focus my attention on. So what I am going to do is I am going to again figure out its middle point. So its middle point is 1. So you can see from index 0 to 1 is the left half and from index 2 to 3 is the right half, correct? And now this index, k equals to 1, this index, where does it lie? Does it lie in the left half or the right half? The answer is it lies in the left half. Because it lies in the left half, so now you will recurse from 0 to 1. And now you know that because this entire thing was 0 and the left half of 0 is 1, the left half of 0 is 0. So you would say that this is going to be a representation of 0, which actually is. Now again, you will recurse. You will say that, okay, now let me figure out the midpoint. The midpoint is 0. So from 0 to 0 is the left half and 1 to 1 is the right half. But my current index belongs to the right half. Because it belongs to the right half, so I'll go from 1 to 1. And now, because I have moved to the right half and this string was a representation of 0, so I know that that will be 1. Now the moment you see that your starting and ending indices both are the same, that means you are pointing to a particular character. And whatever is this value, that value itself will be the answer for the character at that position. So what is this? This is just a simple recursive approach. This was a beautiful recursive pattern and we could apply it as it is. You can take another example. Let's say if the value of k was something like 6. In that case, if you would have started your journey, you would have moved here and you would have changed your value from 0 to 1. Because you know that if this entire string represents 0 and you have to move to the right part, so the right part must be a representation of 1. So that's the idea. So we are going to keep a track of the starting and the ending index, and every time we'll find the mid, and comparing with k, we will get a knowledge whether we have to move to the right part or we have to move to the left part. If we have to move to the right part and the current string was representing 0, then we will toggle it to 1. And if we are moving to the left part, then it will continue to be 0. Okay, if our current string was 1, then the things will be vice versa. It will just be the reverse of whatever it was. Does that make sense? How many of you understand this point? Didn't understand how every string is a representation of 0? It is no, because every string is being generated from 0. You can take any string, and if you deconstruct it, deconstruct means if you compress it, it will become 0. Because it came from 0, it will go back to 0. Let's look at this, no? 0, 1 goes back to 0, 1 goes back to what? 0, which is this. 1, 0 goes back to 1. 1, 0 goes back to 1. 0, 1 goes back to 0. 0, 1 goes back to 0. 1, 0 goes back to 1. And 0, 1 finally merges to 0. That is the idea. Every string, literally every string, is nothing but a big 0. And the left half of it is 0 and the right half of it is 1. Now if you are talking about the right half, which is 1, its left half is 1 and its right half is 0. Because that's how the construction happens. Everyone clearly understands the idea, right? So now if you have to code this question, there is nothing special from the coding perspective. I would say, let's say there is a function func. This is your function func. And it takes the starting index and the ending index, and it returns you the character which is there at kth position. Starting index to start with will be 0. When you make this function call, you will pass s as 0 and you will pass e as 2 raised to the power n minus 1. N is your input, right? And now, how will your code look like? So what was our termination condition? We also saw that at the termination condition, the value of s and e became equal, right? Now, the moment the value of s and e became equal, what was our answer? Whatever was the value of our string, that was our answer. Now one more thing, we also need to pass the value of our string. So we can have a thing value, which is, this is either 0 or it is 1. This is either 0 or it is 1. It can be an integer also. You can just pass it as an integer and then you can probably typecast it or do something about it. So the moment s and e are equal, we will simply return whatever is the value of val. Okay. Otherwise, what we are supposed to do? We are supposed to find out the midpoint, which is going to be s plus e by 2, right? And now we will compare k with the midpoint. So if the value of k is smaller than equal to m, so see, what is the situation? S denotes the starting index, e denotes the ending index, m is the middle index. So if your k is smaller than equal to m, that means your answer lies in the left half. If your answer lies in the left half, what will you do? You will end up making a function call func from s to m. You will pass your k as it is. But now how should your value change? How should your value change? Your value should change depending upon whether this currently was 0 or 1. Because if it was 0, then going to left means it should be 0. And if it was 1, then going to left means it should be 1, right? So that is the idea. So you know what I can simply do here is, I can just put one more check. In fact, inside this thing, I can put one more check to see what my value is. And depending on that, I can make the next call. So just in order to show you, I can say that, hey, if at this point of time, let's say my value was 0. If my value was 0, if this entire string was representing a 0, then the left half of it also represents 0. So in that case, I am just going to call func of s to m. The value of k will be exactly the same, right? And that val will be 0. So I'll return this thing. In the other case, what I am going to do? In the other case, I am going to return func of, I am going to go in the right part, right? So my right part will be from m plus 1 to e, k will be as it is, and my right part denotes 1 now. So this is the condition that I have written when my k is smaller than equal to m. Okay, in the other case, what I'm supposed to, sorry, this part is to be written a little differently, because this part is still for the case when your k is smaller than equal to m. So in this case, you will return func of s to m, k and 1, right? Because if your value is 1 and if you're going to the left, then the value does not change, it remains as it is. Similarly, you can write another condition. That condition will be written for the case where your k is actually greater than m. So if your k is greater than m, that means you're going to the right part. If you're going to the right part, what does that mean? That means that if your value was 0, the right part is going to denote 1. And if your value was 1, the right part is going to denote 0. So that is the kind of code that you can write. There is a lot of scope of refactoring the code. I mean, instead of putting so many if-else conditions, you can have a simple check through which you can toggle zeros to 1 and ones to zeros pretty easily. I'll give you hints around that. But before that, is the idea clear? Could you relate with how even this question was a question of recursion and how the patterns have been deciphered? Yeah? Okay, great. So I would say now that you have clarity on the idea, just go ahead and implement it. I don't want to write the complete code here because if I just write it, it will sabotage your learning. So go ahead, write the code, and you can use your comment section on this video to put your code there if you have coded it. I can even look at the code and give some feedbacks. And even if you are stuck, you can ask for help. You can put your code there. I can look at it and I can suggest probably what needs to change. Okay? I really hope that this session would have helped you understanding recursion better and applying it to a question like this. And so when you go back, just revise all these concepts until our next class. Okay? Cool then. So that will be it. Good night for today, and let's see you all soon.